Hello friends, welcome back to my channel FRM Unplugged. Today we will be continuing with our question bank series on the book 2 of FRM part 1. The book 2 as in the quantitative analysis. So we have seen so far probability, distribution, univariate, multivariate. Now today we will do some basic questions on hypothesis. So hypothesis is basically all about testing a premise. So as a statistician or as a researcher, we would kind of have often come across a data set where we can form an opinion based on the data set, but we have to be clear whether whatever we are having the opinion, whether we can test it properly, and accordingly if we are able to accept the results of that test. That is all about hypothesis. Just because I select a group of IIT Kanpur pass out students and I find that their average mean salary is, let's say, 24 lakhs per annum, I can't just say that okay, since the sample mean converges to the population mean when the sample is large, so this 24 lakh will eventually hold good for the population. But it's not that way. We have to maybe accept this 24 lakhs as a indicative of the salary of the entire group, with some probability that okay, till 80%, 90% probability, this is how it will be. So 90% of the students will have, let's say, 24 lakh annual salary. So like that. Now, there are, if we go to the LOSs, no? So the LOSs are broken down into, let's say, comparing the appropriate null and alternative hypothesis, then differentiating between a one-sided and two-sided test, defining what is the power, type 1, type 2. So my approach to this is, instead of discussing these concepts theoretically, if we are able to solve a problem and during the solution of the problem, we will try to highlight or we will try to discover what is the concepts that we are required to be learning here. Because these LOSs in a standalone basis won't make much sense. All these LOSs will be combined and then only we can make some sense out of it, because the entire story in this particular case, it can't be just like broken down into independent units like we did for probability. So in probability, conditional probability, mutually exclusive events, all those we could separate it. But here, it's not possible logically. So we will look into a problem and then we will try to solve it. Okay. Now, since we are, so hypothesis in our exam, we will always get problems like which are related to the financial sector. Okay. Maybe returns on a bond or something like that. But for the time being, I just wanted to make it a bit easier at the start. So I have taken a non-financial example, right? There are n number of financial examples across the vast literature, but I have intentionally taken a non-financial example so that our mind is not too much closeted on the financial aspects, and it helps us to realize it helps us to understand how the entire concept works. Otherwise, we will keep thinking, okay, oh, this is var. Okay, var's formula is that. No, var is this. Then this is the expected shortfall. All those things will come in. Then we will lose sight from the hypothesis itself. So, okay. So, if we take one problem, right? So, if you see here, now Brinell is a hardness scale. Okay, it is used to define the hardness of certain metals or rocks. Okay. Now, just like a Richter scale measures the intensity of earthquake, a weight measures the kind of mass of the body. This scale measures the degree of hardness. That's all. We don't need to get into any more deep into it. Now, here what the researcher is saying is, the researcher is saying that, okay, he or she has taken, let's say n is equal to 95, 25 is the sample size, okay. So, now, so 25 is the sample size and standard deviation is equal to 20, okay. Standard deviation is 10, and what he is hypothesizing is mu is equal to 70, 170. 170 is the value of the grindness scale, and that person hypothesizes that the average, so this is a sample, mind you, okay. He hypothesizes that the average value of this scale is 170, and he rejects this if the scale is more than 172. Okay. Keep this in mind that the population mean for now is unknown, and which is very logical, right? Whenever you are doing such kind of hypothesis testing, 99% times you will never have any clue of the population mean. Otherwise, then that is the purpose of your testing. No, if you would have known the population mean, then it's a different thing, correct? So in this case, what we will do is, so it is the alternative, the null hypothesis is mu is equal to 170. And the alternative hypothesis is mu is greater than 170, right? And you here the null, you can also write it as less than or equal to, and this is greater than 170. So here the null hypothesis is mu is 170, and the alternative hypothesis is mu is greater than 170, right? Now, what are we asked here? That if the engineer decides to reject the null hypothesis, if the sample mean is 172 or greater, what is the probability that the engineer commits a type 1 error? Okay. So let's say like this. This is the sample or population mean. So obviously he is not aware that he is not aware about the actual population mean, but he thinks that okay, the sample mean is 170, and that's what he is testing, how much we can take it at up to 170. So here let's say it is 172, right? So here it will be 173, 180, like that, right? So like we know, this will follow the sample means this is the distribution of the sample mean. So this will follow a normal distribution that we all know. You could have done this by the t distribution also, because there we will come across that for sample size less than 30 it is t, for more than 30 it is normal. But the normal distribution assumption for less than 30 works as well. Now here what we will do is, so first of all, this is a one tail or a two tail. This is obviously a one tail because we are taking this as 170 and the alternate is more than 170. So this area is the area of rejection. If the value of the sample, let's say he will take many of those 25 samples. This 25 sample, this is let's say 175. Another 25 sample, this is 173. Another 25 sample, this is 169, like that. So what we will do is, we will then calculate the test statistic, right? So what is the test statistic here? Test statistic is the sample statistic minus the hypothesized value of that we are testing divided by the standard error of the test statistic. This is the basic formula. So this is, so more than 172 minus, so we are trying to find the z value, equivalent z value here, right? Because only when we are getting the z value we can figure out the probability. We are asked what is the probability. So for finding the probability we have to normalize the, or we have to standardize the normal distribution. So 172 minus 170 by 25 by n by, standard deviation by root 25, right? This is the standard error of the sample mean. This just says how much the sample mean deviates from the population mean. So we are dividing it to properly scale the difference between the sample value and the hypothesized value. So if we do this, this is 2 by 10 by 5, which is 1. So if we take the, in the z table, if we take z is equal to 1, we will find the z value as 0.8413. Okay. So obviously 0.8413, we know in the z value it is this area is 0.84, right? So this area is 1 minus 0.8413 is how much? 15 point something. This is the percentage of cases when this guy will reject the null hypothesis even though it is correct. See, it is basically 170 is the mean average. So there will be 171 here, 171.51. So major part of those sample mean will fall here. There is only a small chance that the sample mean can fall in this region when we are rejecting. So type 1 error is basically we are rejecting the null hypothesis when it is actually true. This is the definition of type 1 error. If you want to have a easier way to understand, to remember this, just think of it like this, that if you are a judge and the person is actually a culprit, but you are, for some reason, either you don't have the enough evidence or there is a difference in opinion amongst the judges or something, you still let that person go scot-free. This guy was actually a criminal, but you have let him away. That is type 1 error, which means you are rejecting it, but actually it is true. Here, if we are getting, here isn't it mentioned that if the sample mean is 172 or greater, I will reject it? Isn't it mentioned here? It is mentioned in this problem, no? That if the engineer decides to reject if the sample mean is 172 or greater. So this 15% is the type 1 error. We will come across it very often, so it is important we know this. And this type 1 error, whatever is this is usually, this is the probability of rejecting the null hypothesis when it is actually true. This is all about the type 1 error. Now let us take the case of type 2, the next part, right? Now, if unknown to the engineer, if the true population mean were 173, what is the probability that the engineer commits a type 2 error? Okay. So this was 170. Here is 172. Now 173, right? True population mean is 173. What is the probability that the engineer commits a type 2 error? Okay. So all this while, whenever the values formed here, this was 15%, in our previous problem we solved this. This is type 1 error. Okay, now let us come to the second part of the question, which is if unknown to the engineer the true population mean were 173, what is the probability that the engineer commits a type 2 error? Okay, so this is what it is. Now all this while he is under the assumption that I will test for 170 and anything more than 172 I will reject. Now actual mean is 173. Okay, here 173, sorry, let's say this is 173. Now so any value of this sample mean, if it is to the less of 172, this guy will accept it. Now he doesn't know that this is sample mean is 173. So this area, no, considering this is the new normal distribution for the revised population mean of 173. Now this portion is basically, when this portion will happen, if the sample mean comes in this region, what will the researcher do? He will accept or reject? He will accept it, right? Because he thinks it is 170 and anything to the left of this is 170, left of 172 is acceptable. So he will accept it, but actually the sample mean is here, 173. So this portion, we have to again find out the z value for this 173. Okay. Now if we do this, now it will be 172 minus 173. Okay. By 10 by root 25 is equal to minus 1 by 2 is equal to minus 0.5. This is the z value of minus 0.5. Now if we see the z table, minus 0.5 is 69.15, right? So this is minus 0.5, this is plus 0.5, right? Minus 0.5. So this portion is 69.15. So this portion is how much? 1 minus 69.15, which is approximately 30%, right? So basically this portion is 30%. Because this is symmetrical, we know that, right? For negative values, how we use the table. So this is 30%. I'm just giving a ballpark figure. It's in decimals. So 30%. Now this 30% is what we call it as the type 2 error. Means we are accepting this value because obviously the researcher still knows the value of the mean as 170 rather than 173. He is accepting it, but actually he should have rejected it. This is what we call it as type 2 error. In the parlance of judiciary, you can keep it, you can remember it this way. The type 1 error was the person was a criminal, but you have let him go without a punishment. And the type 2 is just the opposite. You have convicted a person, but he was not the criminal. So from this scenario, this judge and convict scenario, which one do you think is the most, more serious, type 1 or type 2? Obviously type 2 is more serious because, okay, type 1 is also serious, but type 2, even if the person is not kind of not a criminal, but you have still convicted him. So this is what is a type 2, this portion. So this is the type 2 error. Now there is a third question also. If unknown to the engineer, what is the probability that engineer makes the correct decision by rejecting the null hypothesis in favor of the alternative hypothesis? So what is the probability? Now see here. he is still under the belief 170. So he will reject the null hypothesis if the value comes anywhere here, all this place 174, 175, like that, right? Because since the actual value of the population mean is 173, he is more likely to get these values rather than these values here. We have to keep this in mind, because the actual population mean is 173. So what is this value? This value entire to the right of 172 is 1 minus this type 2 error, which is how much? 30% was there, so this is 70%. This 70% is the probability that the researcher will reject the null hypothesis, because the null hypothesis is actually false. So this 70% is also called the power of the test. Power of the test has to be more when you are able to reject it when the null is actually false. Bigger the power of the test, lesser is the type 2 error. How do you see? We have to reduce both type 1 and type 2 error. Type 2 error, how will we reduce? We will reduce, just look at this graph, no? The more you shift this to the left, the more the area here becomes, the more the power of the test. So a good hypothesis test will usually have more power. This chart, no, it is there in any statistics book you open, any book you open, you will get this, okay? Now, accept, reject. Okay, here null is true, null is false. Okay, when it is true but I am rejecting it, this is type 1, right? If it is false, so this is null hypothesis. If it is false but I am accepting it, this is type 2. Now, this is probability, right? So this probability is 1, this probability is 1, okay? So this is the power of the, so this is the type 2 error, and this is the 1 minus probability of type 2. This is equal to power of the test, okay? Because we just saw it from the diagram, the more we were shifting it to the left, the more the power was becoming, and lesser is the type 2 error, because sum of the area under a standard normal curve is 1, right? It is akin to the theory that the sum of the probabilities is 1. And this is, if we are rejecting it but the null is true, this is type 1 error. And when I am actually accepting it and it's true, this is 1 minus type 1. So this is the correct decision. And this is also called the significance or alpha. Just remember this way. Any normal, this portion for a one-tailed tail, this is alpha. If it is two-tailed test, sum total of these two is alpha. Simple. So I think this problem should serve as a guidance for most of the concepts of hypothesis, and we will shortly see more numericals which will even fine-tune and develop our concepts. With this, we come to the end of this session. We will soon come up with another analysis, another question bank for hypothesis. Thank you.